Well, good morning. Thanks for coming in. We are in section 714 today, and we're going to talk about this idea of flowchart proofs, and we're going to formalize some of the stuff we discussed yesterday. So we're going to continue using them. And one of the things that is true in a flowchart proof is we have these ideas that are interconnected with each other, right? And the connections are shown using these arrows. So inside of each one of the ovals, right, we make we make a statement. We assert something is true, right? So in each one of these, we have statements, and we assert that it's true. The truth of that statement typically requires, on this case, this statement where it's at, it would require some supporting evidence, some supporting ideas, and those are flowing into this statement. And also, there needs to be a reason that's written off to the side of the oval. So every single one of these is a statement followed by a reason. And what I want to do this morning is I want to give you and have you get in your notes a list of reasons, a list of things that you can use in this specific place, in the reason space. And we won't always do flowchart proofs. There's other kinds of proofs we'll look at as well, but they're always going to need statements, something that you're asserting is true, and why you're saying that's true. What's the reason you have for it, and then the supporting evidence for that. So let's take a look at a list of reasons. I'm just going to write this out. So reasons, REASONS. So let's build a list of reasons. Well, one of them, and you've seen me use this, is given, right? So on the diagram, for example, I might be given an angle measure. I might be given a side length. I could be given that things are congruent, right? I could be given congruence. And that would be because I could be given congruence, like just when you read it from the diagram, you see the tick marks. So that's something that's pretty straightforward, right? It's given. Another one that we mentioned yesterday is the triangle angle sum theorem. Theorem. It's basically just states, and it was in our text, that the three angles in a triangle add up to 180 degrees. Another possible reason for a justification could be the Pythagorean theorem. So like if you knew two lengths of a triangle and you wanted to assert what the third one was, you could say, hey, this side is 5. Why? Because of the Pythagorean theorem and the lengths of the other two sides. So the Pythagorean theorem could be a reason. We could also have some definitions. So definitions, and there's several definitions here. Let me clear this out of the way. So some of the definitions we know is like the definition of congruent angles. Basically just says definition of congruent angles said two angles are congruent if and only if they have the same number of degrees. Definition of congruent segments, right? So if you've got two segments that are both 10, you could say, hey, those segments are congruent. Not congruent angles again, congruent segments. segments. Two segments are congruent if and only if they are the same length. Another thing is like the definition of a congruent triangle, right? So if two triangles are congruent, you end up getting 6 things are true. So if you can show that triangles are congruent, there's six things, 3 pairs of sides that have to be congruent and 3 pairs of angles that have to be congruent. So 6 things are true if you have congruent triangles. If you want to show two triangles are congruent by the definition, you have to show all 6 things. So this is like the first way that we talked about how do you get congruent triangles. You have to show that 6 things are true. And then we came up with a shorter list of ways that you can show triangles are congruent, and the only 2 are the angle side angle and the angle angle and then the non-included side. So this list of triangle congruence things, there's going to be more to come, but we're going to leave it at just those 2 for now. Another thing that is a reason, and this will show up in some proofs in the near term, is something we'll call the reflexive property. And the reflexive property basically says there's technically there's a reflexive property for congruence and a reflexive property for equality. Basically, a thing is congruent to itself, and a thing is equal to itself. And so, like a segment that's 12 is equal to itself. So I'll just write a thing is congruent and equal if it's something that's measurable to itself. And you're probably thinking like, well, why in the world would that ever happen? Let me give you a quick for instance. If I look at this diagram right here and I'm asked to prove that these 2 triangles are congruent, first of all, let's be clear, they don't look congruent at all, but I think that's because although these angles are marked as congruent by the tick marks, and I'm going to go with they're congruent because of the tick marks, the problem that we have is that there's not enough information, right? We've got these are right angles, therefore they're 90 degrees, therefore they're congruent, right? So we've got those congruent angles, and we've got these congruent angles, but no sides, except we can point out that DB is congruent to itself. And the reason why that's helpful is DB is in both the top triangle, the one above, and it's also in the triangle below. So that's where the reflexive property comes in. If you want to say, hey, I actually have a side because these triangles are touching, DB is congruent to itself by the reflexive property. So that's a thing we can say. Let's see, what else? There's a lot of properties that involve alternate interior angles and parallel lines, and we probably should, let's just make this a whole category here. So if we have a pair, so these things apply to if you have 2 parallel lines cut by a transversal. So we need to have parallel lines. Let me sketch something over here. So we need to have parallel lines, but if we have parallel lines that are cut by a transversal, right? That means it goes through both of them. Whenever 2 parallel lines, and I'll mark on here, this is parallel to this one. So these are indicating they're parallel. When 2 parallel lines are cut by a transversal, there's a lot of things that are true. You've experienced this in the 7th and 8th grade. You've seen these things, but some of the things that are true is this angle right here and this angle. Those angles are called corresponding angles because they're in the same location, right? So if 2 parallel lines are cut by a transversal, then all of the corresponding angles are congruent, right? If 2 parallel lines are cut by a transversal, corresponding angles are congruent. Alternate interior angles are congruent. Alternate interior angles are congruent. Let me give you an example of some alternate interior angles. Let's put a little. I'll put a little purple mark right here. Corresponding angles. Alternate interior angles would be something like this angle and this angle. They're on alternating sides of the transversal, and they're inside of the parallel line. So those are called alternate interior angles. And whenever the parallel lines are cut by a transversal, those would be congruent. So those are alternate interior. And I'll just put down one, I guess another thing. It's true that alternate exterior angles let's see, what about alternate exterior angles? Oh, so like I could say this orange angle right here and this orange angle right here, those are on alternating sides of the transversal, and they're outside of the parallel lines. Those alternate exterior angles are also congruent. So these are just some ideas, right? And I want you to have this list, and as you discover or you come across other things that you see in proofs, add to this list so that when you're thinking about what the heck can I put outside of my ovals here for reasons that are things are true, you've got a place to look for a list that you're building out. We're just going to finish now with a couple of proofs, and these actually appear in your textbook. And we'll look at this one right here. So the instructions say, hey, tell me whether or not these triangles are congruent. And if they are congruent, give me a proof for it. Well, right now, the only two things that we're looking at for triangle congruence are angle, angle, and then a side, a non-included side, or the angle, side, angle. So these are the only two that we're looking for. And I think even if I look for more, I don't see that here. And I can't use any of the other ones that are outside of angle, side, angle, and angle, angle, side because they would fail also. And I think that the deal is it's the reason, the limitation with this is that we don't have any information about this side length. If I knew that was 4, that might change my mind. But not knowing that that's fixed at a particular length, I could draw this so I could say, well, this thing right here, I don't know how long that is. So I could make it much, much longer. And if I make it longer, I could change this side too, right? So here's the thing. By me pulling this side out and making it much longer, I haven't violated any of the information in the diagram. I still have the 6 and the 6 and these two congruent angles, right? But it's very clear visually that these are not congruent triangles. So on this pair, I would say no, they're not congruent. So let's not write anything down for that. On this one, let's go ahead and do a flowchart proof for this. And it's going to have some extra interesting pieces. So let me first of all make this pen a little bit thinner. And let's see if we can't do this. So one of the things I pointed out was there is the reflexive property at play here. dB is congruent to itself, so I'm going to be able to point out that I've got that side in both triangles. And what the triangles I'm trying to prove are congruent is the one that lives above and the one that lives below. I want to show that those two triangles are congruent. And it's very close to angle, angle, side, so I'm going to start with that idea. So I'm going to start with a couple of ovals here. One of the things that I think I need to talk about too, and it's a nice opportunity for this, is if you look at angle D, if I said angle D, we wouldn't know which one I'm talking about, right? Because there's an angle D above, and then there's this one below, or do I mean the entire thing, right? Same thing with angle B. If I was to try to talk about angle B, I wouldn't know which angle you're talking about or I'm talking about because that's at that vertex B, but this is at that vertex B, and the whole thing is at the vertex B. So when we get to where we talk about angles that are ambiguous, like this one, if I wanted to talk about the top one, I would have to call this angle A to B to C. So we always do this so that the vertex, the point of the angle, is in the middle. So I could refer to that top angle, no, not ABC. ABC would be the entire thing. If I want just the top one, it would be ABD. So ABD is just this top bit of the angle. That's what that is. If I wanted to talk about the bottom bit of the angle, I could talk here about angle C, and then the vertex in the middle, B, and then D. So C to B to D is speaking about this angle, right? So CBD is that angle. Maybe if I color code them a bit, I'll put a little orange dot here. And this is ABD. And I could put a little green dot here. And this is CBD. Now those names could be switched, right? I could alternate the A and the D. So this is the same as talking about angle DBA, Right? The important part is that the vertex is in the middle there, or I could refer to this lower angle as angle D and then B and then C. Okay, so if I want to talk about, this is a big idea, and I'm glad we're talking about it. If I want to talk about these angles and it's not clear what angle I'm talking about, I have to use 3 points to name the angle. Now, if you look at angle C, there's no reason why I would have to do that. Angle C is clearly just, there's just one angle there, so C is a fine angle name, right? Another thing I can do if I want in my diagram to facilitate things, I could say that this is angle 1 and this is angle 2. I could call this angle 3 and I could call this angle 4. So this is an alternate way to kind of make it clear which angle we're talking about. I'm just numbering my angles and I can refer to the diagrams that way. And I really should be able to do and use both. So let's start with this. So if I want to talk about angles, the ones I labeled angle 3 and 4, I could say angle 3 and angle 4 are right angles. And that's given, right? In the diagram, that square marking tells me that those are right angles. It doesn't say they're congruent angles, but come on, we know they are because they fit the definition. They're both 90 degrees. But they're given as right angles. And I could then come in and I could say, look, because they are right angles, right, I could say that angle 3 is congruent to angle 4. And I know that we used to do this. I used to write this in the past. I would say something like all right angles are congruent. It's nice if we have little small reasons. By the way, that's something I could add to my list of reasons, right? I could always say all right angles are congruent. So at this point I have a pair of congruent angles. I don't have a pair of congruent sides, but I'm going to quickly get it. I'm going to say that segment DB is congruent to segment DB. And the reason, right, something is congruent to itself. This is the reflexive property. Reflexive property. Fabulous. Fabulous. So I now have, oh, these are kind of all in the way here. Let me get this out of the way. I now have a pair of congruent angles and a pair of congruent sides, and I got the other set of angles on the other end. And just to demonstrate this, I'm going to name these angles using the 3 vertex thing. So I'm going to, angle 1, the one on top, is angle A to B to D, and that angle is congruent to angle, and then the one below is CBD, C to B to D. And that actually, because of the tick marks, I can say that that's given, right? It's given that those two are congruent to each other. All right, so you can see the pattern that I have here. We've managed to get the angle side angle pattern. So we can now claim that these two triangles are congruent. We're going to say that triangle ABD, A to B to D, is congruent to, that's ABD, is congruent to triangle, and I'll go C to B to D, triangle C to B to D. And the reason those two triangles are congruent is we establish the angle side angle congruence condition. Congruence condition. All right, so then the supporting evidence. Where's your pair of congruent angles? Well, here's a pair of congruent angles, right? Angle 3 and 4 are congruent. Where's your pair of congruent sides? Here they are, my congruent sides. And where's your pair of other congruent angles on the other end? There they are, right there. So we're going to finish it right here today. We're almost at 20 minutes. So the big thing I want to see in your notes is I would definitely want to see this. And I definitely want to see a list of reasons, right? A list of reasons. I want you to start developing, building out a list of reasons that you can use in proofs, things that you know are true. Some of them can be theorems, some of them can be things from your 7th or 8th grade year that you know, especially with the corresponding angles. But just this one proof and the reasons, and then also the big idea here that when we're using a flowchart proof, right, they always contain statements. There's always statements in the ovals, and then in addition to the statements in the ovals, we have reasons that sit outside of that. All right, this is Mr. Roberts. I hope you have a great day. I look forward to seeing you tomorrow in class and online, and we will be doing the Chapter 6 test this week, and this Thursday, Friday. I'll see you soon.